here, we found that B is equal to E. E is the what? Eccentric offset distance of the applied axial load. We substitute into that equation again. Okay, in equation 4, it will not get any worse, okay? Then from here, we use our what? Second what? Boundary condition. And then we have this relationship. From here, we tend to acquire, we determine the constant A, right? So we want to find constant A. I'm not a genius. I did not figure this out. I read the textbook, okay? So they say use double angle. So you know that sine 2 theta is 2 sine theta cos theta. Okay, we're going to let 2 theta equal to PL. So that's equation 6. Then we're going to use sine 2 theta is equal to sine PL. Okay, so it's 2 sine PL over 2 and cos PL over 2. Then we're going to use another double angle relationship, cos 2 theta, because we have cos PL over, oh, don't do that. It gets worse. Can I wipe it away? No, I cannot wipe out the highlight. Can I wipe out the highlight? No, sorry. Then from here, okay, we substitute things into equation 7 and 8. And then we found this relationship where what? A is equal to E tangent theta. Now going back to our unique solution, y as a function of x. So we substitute, we know our A value, okay, we know our B value. So we know our A is equal to what? Our A is equal to E tangent PL over 2, our B is E. Factor out of B, then we use the relationship. Okay, as I said, Y max is equal to what? X is equal to Y over 2. You work out a bit of math again. Now, this is nothing compared to your 2ZZ03 or 2ZZ07, whatever you take, okay? This is just trigonometry and substitution, okay? We found a relationship that we have Y max. Now, this is where we start to see the what? Secant. We clear, okay? Holy shit. Then we want to find Y max, okay? Y max will occur when what? When the lower, when the factor or when the coefficient at the bottom is equal to 0, because 1 minus 0 tends to infinity. So from here, we know that Y max is equal to what? Pi over 2 PCR, P over critical load minus 1. Then after that, we use, does this look familiar? This is to calculate the stress. Okay. And the maximum moment now is equal to what? Y max plus E. So again, this is due to the eccentric. This is due to the deflection. You put everything in, finally, you have a relationship like this. Okay, so this relationship is just geometry. Okay, it's just geometry. I don't want to bore with you by making you write 3 pages. At the end of the day, we're back to square one. Okay. Now from here, okay, so now we have to start copying. Okay. So with this expression over here, we know that tau max is equal to P over A 1 plus by EC over R squared secant pi over 2 square root P over P critical. And we know that P critical is equal to what? Our P critical is equal to pi squared EI over L squared. Okay, we know that relationship. So we're going to substitute the yes. No, there's no A because it's critical. I make a mistake on Friday. Okay. So stress max is equal to P over A 1 minus EC over R squared secant. We have pi over 2. And then we have square root. And then P, and we're going to put P critical is pi squared EI. And this is equal to what? This is over L squared. Okay. I don't know what is happening, but okay. So now we can get rid of our pi. Okay. So now we can put in our P over A. I think I might be okay, it's okay. So P over A 1 minus EC over R squared secant L. So I'm going to bring out L over 2. And this term will be equal to P over EI. And then I'm going to say note again. Note that I is equal to A R squared. Yes. Did I? Oh, it's positive. Thank you. So from here, we have P. Thank you so much for telling me. Okay. It's 1 plus by EC over R squared secant L over 2, and then P over E A R squared. And then we close another bracket. And then finally, we have this relationship that we will be using. Now, a thing to take note is that this term over here is in radians. What does that mean when I write that? Anyone? Yes. Yeah, you need to click the button. 2 years ago, I told the student that this is radian. Student put up their hand, what is radian? Oh yeah, he was so lucky there are a lot of weakness around. Or not, I would have done something. Yes. What do you think? I'm still thinking. I'm not that evil, okay? I might have anger management, but I'm not evil. Right. So this is the formula, okay? And it's nothing scary. So he says. Let's do an example on eccentric buckling. Now, this buckling thing that we are learning, okay, in 3E03, this is going to be the first topic that you will learn in buckling, okay? So don't throw these notes away. Right. Let's look at this question now. Okay, and I've posted this question for you. And then this is our, it's nothing difficult, okay? It's not difficult at all. It's really not difficult at all. It's quite, I think I post this on Friday, if I'm not wrong. Okay, watch here. Now, this question, okay, entails eccentric buckling, okay? The steel column support two eccentric, two. Okay, wow, okay, scary. Two eccentric loading. It is assumed to be pinned at its top, right? So we know over here when it's pinned, moment is equal to what? 0. And fixed at the bottom. We know that M is not equal to 0 now. And fully braced against buckling about the YY axis. Okay, about the YY axis. So this question, you have to step back and think a bit, okay? Now, the transformation is given in this form already. So that is the what? Transformation. Okay. So when that's the case, this will be your Y. This will be your Z. And the rotation will be your what? X. Agree or disagree? So i.e., what you see over here is known as the plan view. And the plan view, we are looking from the top. Okay, we are looking from the top. Are we clear? This is your eye, okay? So this is the plan view. And then this is our what? Front view. Make sense? Yes or no? Okay. So now, it says that buckling is braced against or the fully braced against the YY axis. What does this mean? So I'm now going to draw the structure. Okay, I'm going to draw the structure in 3D now. Okay, I'm going to draw the structure in 3D. So this will be my Y. This will be our Z. And this will be our X. Okay. So if I'm going to sketch this out or X, yeah, it can be in that orientation. Okay. So if I'm going to sketch this structure out, it will look like this. Okay, I'm going to sketch a structure out. Okay. So this is how the structure look like. Okay. If buckling were to occur on the YY axis, okay, YY axis means what? Can you visualize if buckling will occur in the YY axis, what will happen? And if buckling will occur in the XX axis, what will happen? Okay, so how to visualize this? Okay, the best thing to do is to sketch the rotation. Okay. What do I mean by sketch the rotation? Over here is rotation about y. Yes? This is rotation about what? X. I will use a different color. Okay. So this will be my rotation about what? X. If the rotation is about y, the buckling, I'm going to sketch in blue, will look like this. Can you see it or no? Yes? Makes sense? If the buckling, okay, so it's flat, okay? If the buckling is about X, it will look like this, okay? It will look like, I'm going to draw it this way, okay? It's going to look at this. So this is flat. So I'm going to sketch that this is flat, okay? So the red one is on this plane over here. So the curve that I draw is flat on that plane. You all get what I mean? It's not a 3D effect. It's a flat that I on that plane. Okay, so this is buckling. Okay, so in red, this is buckling about the what? X what? Axis. Why? Because it's rotating about the what? The x-axis. Okay, the other one. So can you all visualize that this the blue line is flat? Okay. So this over here is buckling about the what? Y-axis. Are we clear? Okay. So I want you to visualize this first. Now, this is a very kind question. In your term test, I'm not going to tell you. Okay. You have to what? Figure out buckling will occur where, which direction. Are we clear? Okay. I'll see you guys in an hour's time. Go and smoke something and get high. Okay.